Okay, we're in Chapter 3, Section 2, Compound and Continuous Compound Interest. And we'll take a look at the first couple of goals here. We'll be able to compute compound and continuous compound interest, and as well as growth rate of a compound interest investment. So, what is compound interest? Well, we've looked at simple interest so far, but unlike simple interest, compound interest on an amount accumulates at a much faster rate. So, the basic idea is after the first interest period, the amount of interest is added to the principal, right? So if you've invested some principal, you've compounded interest on that principal, and that interest is added to your original principal. Okay? So then the interest is computed on this higher principal because now you have a higher principal. Well, the latest computed interest is then added to the increased principal, and then interest is calculated again, and we continue this process over and over and over. So the result is just a much faster growth of money than simple interest would give you. So here's an example. Suppose you start with $1 American dollar. How basic, right? Just $1. A principal of $1 was invested in an account, right? So this is principal $1 invested in an account paying 6% annual interest compounded monthly. So my annual interest is 6%. Written as a decimal is 0.06. It's compounded monthly. Okay, there's 12 months in the year, remember that. How much would be the account after 1 year? Well, using the simple interest formula, let's see what happens month by month here. So we'll use this formula, A equals P times 1 plus RT from the last section, and we'll see what happens. So P is 1 for us, right? So we're really multiplying by 1. The rate is 0.06. The time is 1 over 12 because we have 12 months here. That make up a year, and that's how we get 1.005. A similar calculation is then done for 2 months. Notice the new principal though is the principal after the first month. 1.005 now becomes the new P for the calculation after 2 months. Okay, multiply that by 1 plus R times T. T is once again 1 over 12 and R is 0.06. Right, so here R is 0.06. T is 1 over 12. They're just written together so that, we save some room. And the calculation gives us 1.005 squared this time. So that's the new principal. So when you start calculating the interest and what's in the account the third month, you start with this new principal. Okay, that's your new P. Multiply again by 1 plus RT. And surely enough, you get 1.005 cubed. Well, you see the pattern here. If we go on after 12 months, 1 year, the amount is just going to be 1.005 raised to the 12th power. That gives you about 1.0616778. Notice that if you were to use simple interest, the amount after year would be simply 1.06. You could calculate this with the simple interest formula that we have. Well, the difference is not that noticeable here. It's very small. However, after several years, it does become more obvious, as you could see from this graph. What we have here is the growth of $1 compounded monthly at 6% annual interest over a 15-year period. So this is 15 years that we've graphed here. The arrow indicates an increase in value of almost 2.5 times the original amount, which was 1. Okay, so this really does take its toll in the long run. That's where you see the difference. Well, in that previous example, the amount to which $1 will grow after n months, compounded monthly at 6% annual interest, was given really by this formula, 1 plus 0.06 over 12 to the n power. Okay, well, they gave us 1.005 to the n power, right, which we plugged in 12 to find the answer for. But this formula can be generalized to the following formula. A equals the principal P times the quantity 1 plus R over M raised to the power of MT. So A here is the future amount, P is once again the principal, R is the interest rate as a decimal, right? So this is the interest rate as a decimal, always, remember this. M is the number of compounding periods. Since we were compounding monthly in the previous example, M was 12, right? But it could be anything. It could be 4 if you're compounding quarterly, 1 if you're compounding annually, 2 if you're compounding biannually, etc. So this is the number of compounding periods in 1 year. Okay? T is the total number of years of your investment. So to simplify the formula, sometimes you'll see it in your book written this way. A equals P times 1 plus I, the quantity to the n power, where I is the R over M and N is the M times T. I am not the biggest fan of this simplification, even though I definitely see the advantages of this So I'll probably stick to the main formula, but you'll see both of them in the notes and in the textbook, so keep that in mind. Let's take a look at this slide that summarizes it. A equals P times 1 plus I to the n, or once again, A equals P times 1 plus R over M to the mt power. Okay? So each one of these variables is explained here. That I, the advantage of looking at that I, that R over M, that I is the rate per compounding period. That's what it's called, rate per compounding period. So oftentimes, instead of writing R over M, they write this I, which is calculated as R over M, and it's just the rate per compounding period. Okay, let's take a look at an example. Find the amount to which 1500 will grow if compounded quarterly at 6.75% interest for 10 years. So as we're reading this, let's make sense of what each statement means variable-wise. Find the amount to which something will grow means we're looking for A. That's the future value. That's something that will grow. The 1500 is our principal. That's what we start out with. Compounded quarterly means that our M is 4. There's going to be 4 compounding periods within 1 year. The 6.75% interest means that R is 6.75%. But remember, we must always write this as a decimal. So as a decimal, this is 0.0675. The 10 years is our time, T. Well, all we have to do now is put it together into our formula. A equals P times 1 plus I over N, or A equals P times 1 plus R over M to the MT. Right? Remember, same thing. And doing so, we get 1500 times 1 plus 0.0675 over 4, that's our M, raised to the power of T times M, which is 40. Well, using a calculator, you can compute this to be 292950. The helpful hint is be sure to do the arithmetic using the rules for order of operations. In fact, let me quickly show you how to do this on your calculator in case you're having trouble entering this. So once again, what I'm entering is 1500 times the quantity 1 plus 0.0675 over 4 raised to the power of 40. So here I go. I start with 1500. I open a parenthesis, okay? And then in the parenthesis, I'm going to have 1 plus, I'm going to open another parenthesis for my fraction. The fraction was 0.0675 divided by 4. 0.0675 divided by 4. I close the parenthesis for the fraction. I close the parenthesis for the quantity, and I raise this to the 40th power. Right, I could do 4 times 10, but I know that that's just 40, so I could just do that in my head. And that's how I get the answer, 2929.50. Right, that's what we had here. Now, one interesting thing to see is what happens. Let's compare had we done the same problem using simple interest. So using the simple interest formula, the amount to which 1500 will grow, same conditions, right? 6.75% interest rate in 10 years. Notice, using that formula now, A equals P times 1 plus RT, simple interest, we get something totally different, obviously, and it's $2,512.50, which is more than $400 less than the amount earned using the compound interest formula. Okay, so compound interest is the better scenario here, and let's see what happens when you change the number of compounding periods per year. Let's investigate this case. So to what amount will 1500 grow if compounded daily at 6.75% interest per year? The only thing that we're changing here is that we're compounding daily. The number of compounding periods in this case would be 365 because we're compounding daily, and there's 365 days in the year. So as you could tell, here is the formula. Nothing changes except my M is now 365. Therefore, the 365 will appear in the power as well, and you're going to get a much different number, 12,945.87. Okay, so since there are 365 days in a year, the number of compounding periods is now 365. Divide the annual rate of interest by 365, right? That's our M. So notice that the compounding periods in 10 years is 3,650. In fact, one conclusion that we could make is that if the number of compounding periods per year is increased while the principal, the annual rate of interest, and the total number of years remain the same, all the other conditions remain the same, you just increase the number of compounding periods per year, then the future amount of money will increase slightly.